Hi everyone. So in this video we are going to see some types of amplifier like voltage amplifier, current amplifier, transresistance amplifier, transconductance amplifier. So it is a very simple topic. We will just see what is the output impedance of a particular amplifier, what is the input impedance of a particular amplifier, what is the gain, all those things we will see. So let's start one by one. First let's just study about voltage amplifier. So what is a voltage amplifier? You will have a voltage input. You are having a voltage input and you will get the voltage output. You will pass it through an amplifier. Let's call it AV. AV shows voltage gain. So this amplifier will give you a particular voltage gain and you will receive some output at some particular node. Basically this portion was your input. This portion was input. This is the voltage amplifier and this is the output. Input voltage amplifier, output. Why it is called voltage amplifier? Because output is voltage, input is also voltage. So voltage amplifier. That's why it is called voltage amplifier. Right? Now let's just make the internal structure of that voltage amplifier. Let's make the internal structure of this voltage amplifier. How will this voltage amplifier look like? So this voltage amplifier, any amplifier will have some input resistance. Not just for voltage amplifier, any amplifier will have some input resistance. Now whatever the voltage coming on this input resistance, that will be amplified with the factor of gain, and in our case that factor is AV. And whatever the voltage is coming, let's just say the voltage coming is V in. The voltage that is coming across this R in resistance is V in, and that is being amplified with the factor of AV. Amplified with the factor of AV, so AV into V in. Now it will have some output resistance as well. This is the output resistance it is having, that is R naught, and now output will be fed to the load. So this much of structure, this much of structure, this much of structure is that amplifier. This is the voltage amplifier. Now let's just make the input and output as well. What was the input? What was the source input? So we had a Vs source input. Vs. What is Vs? Vs is there from a particular node to ground, because Vs is written. So this Vs voltage is with respect to the ground only, right? So we have a particular voltage Vs, and that voltage has some source resistance Rs, and that is connected to the load, and that is connected to the amplifier, not to the load. That is connected to the amplifier. So basically some amount of Vs is going into the amplifier. So this portion will be grounded because we are taking Vs from the ground only, right? So some portion of Vs is going to the amplifier. What is that portion? What will be V in? Tell me. V in will be R in upon R in plus Rs into Vs. Now that portion is being amplified and it is being fed to the output, and in the output at the load we are having RL. Well and good. So what will be your output? Tell me. It would be AV into V in, AV into V in into RL upon RL plus R naught, right? RL upon RL plus R naught. Simple potential division. That's it. So V naught will be equals to AV into, what is V in? V in is R in upon R in plus Rs into Vs. This is your V in, and rest portion is RL upon RL plus R naught, right? So what is your V naught by V in? What you are getting as V naught by V in? What is your total gain? Total gain is some gain that is being applied by the amplifier only, AV into R in upon R in plus Rs into RL upon RL plus R naught. So this is the gain you are getting. Now what is in your hand? What is in your hand? In your hand there is amplifier. You have the amplifier thing. You can change the R in resistance, you can change the R out resistance. RL and RS you cannot change, because RL is the load that is being applied and RS is the source resistance that will be there. So tell me, what should be the value of R in so that I get the maximum output? What value should be there for R in so that I get the maximum output? Because you are using it as an amplifier, so you want the maximum output. So what should be the value of R in so that you get the maximum output? Tell me. R in should be infinity. If R in is infinity, that means the complete Vs will be coming across this, and the complete Vs will be amplified by the factor of A. The complete Vs will be amplified by the factor of this AV. If R in is some value, then what will happen? The Vs will not be coming at the input. V in would be R in upon R in plus Rs. It would be some value, but that value will be lesser than Vs. That's for sure, right? And if Rin is infinity, what will happen? Put Rin equals to infinity here. So Rin is infinity. If Rin is infinity, then Rs would be very small with respect to Rin. So Rin upon Rin. So it would be 1 only. So Vin is equals to Vs. So directly Vs is going towards the input of the amplifier. Vin is going towards the input of the amplifier if Rin is infinity. So for an ideal voltage amplifier, for an ideal voltage amplifier, Rin should be infinity, right? Yeah, Rin should be infinity. What about R naught? Tell me about R naught. What should be the value of R naught so that you get maximum output? What should be the value of R naught so that you get maximum output? The value of R naught should be 0, because you don't want R naught to eat up any voltage. What is your V naught? V naught is RL upon RL plus R naught into AV into VE. RL upon RL plus R naught into AV into VE. If your R naught is 0, then what will happen? RL by RL into AV into VE. So it would be 1 only. So complete amplified portion is coming at the output. Complete amplified portion is coming at the output if your R naught is 0. Well and good. So for an ideal voltage amplifier, R naught should be 0. Now people will say, sir, RL should be infinity. Okay. If RL is infinity, then also complete portion will come. Yeah, that is fine. RL should be infinity. But we are talking about the amplifier. So I will only talk about Rin and R naught. I am not going to talk about Rs and RL. If Rs is 0, then what will happen? Vs will be equals to Vin. If Rs is 0, then Vs will be equals to Vin. But I am not talking about Rs here. I am not talking about RL here. I can change Rin and R naught value. So I will pick an amplifier which has the maximum Rin value and minimum R naught value so that I get the maximum output using that amplifier, right? So I will pick that amplifier that has the maximum Rin value and minimum R naught value. Maximum Rin, most of the part will be coming to the input and that will be amplified, and amplified output will be going towards the final output. The amplified input will be going towards the final output if your R naught is 0, right? So this is the scene. Very easy thing, very easy to remember as well. You can think in your brain only, okay, if you are talking about voltage amplifier, that means I need the maximum voltage, so Rin should be infinity. If the maximum voltage is coming, that means I need the minimum R out, so that maximum amplified voltage should be going towards the output. That's it. So this is the thing that you need to remember. Or you can say that Rin should be high and R naught should be low. This is also said. Okay. So if Rin is infinity and R naught is 0, then what will happen to V naught by V in? V naught by V in would be equals to, if Rin is infinity, it would be 1, and if R naught is 0, it would also be 1. So V naught by V in would be AV. So the gain that you are having, so the amplifier will have the same gain that it was supposed to have. But since it is having finite R in and finite R out, you will not get the same gain. Let's just assume you went to a market, you said that, sir, I need a gain of 10. I need a voltage amplifier which has the gain of 10. But you don't know what is R in there, what is R not there. You don't know what is the input resistance of that particular amplifier. You don't know what is the output resistance of that particular amplifier. So when you connect it to a source and then you connect a load there, what you would expect? That your output should be 10 into Vs, right? This is what you are going to expect. Here I should not write V in, it is Vs only. Sorry. V naught by Vs I am writing. V naught by Vs. So you are applying 10 volt input and you would expect 10 Vs, but it will not happen because there will be some loading. What will be your output? Output will be 10 into Rin by Rin plus Rs into RL upon RL plus R naught into Vs. That will be your final output. So based on Rin, Rs, RL and R naught value, you will see what will be your output. Well and good. Let's move to the next amplifier. What is the next amplifier in our series? That is transresistance amplifier. What do you mean by transresistance amplifier? What is resistance? Resistance is voltage by current, right? So output will be voltage and input will be current. Voltage by current. What is resistance? Voltage by current. So input will be current. Input will be current. Now, okay, let's make it. So first let's just make the amplifier only. This is our amplifier. Here I am going to write Rm as the gain. Rm as the gain. Here your AV was the gain. What is the unit of AV? Unit of AV. Output voltage divided by voltage. Volt per volt. Or you can say unitless as well. Output voltage, input voltage, volt per volt. Volt per volt. Here the unit will be volt per current. Voltage per ampere. So you can call ohm. The unit will be ohm. Voltage by current. What will be the unit? Ohm. So that's why I am showing it with Rm. Okay. I'm going to show it with Rm. Now what will be fed to it? What will be the input? Input should be the current. So Is is the current source that I am having. Now this current source will certainly have some resistance. That resistance is Rs. Now at the output you will have some, what you are having, in the output you are having some voltage. So in the output you are having some voltage. So this is your output and you are having some voltage. You will connect it at a load. Well and good. So what should be the internal structure of this? Let's make the internal structure. So what should be the internal structure? It will have some input resistance. Now what will be coming into this input resistance? What will be coming here? A voltage or a current? Certainly if there is current, there will be voltage as well. If there is voltage, there will be current as well. But we will write in terms of current. Why so? Because here what I was writing in terms of voltage, that voltage is coming and that is being amplified. Here the current is coming and that will be amplified. So here the current would be coming, that is I in, and that will be amplified with the factor of Rm. The current would be amplified with the factor of Rm. Rm into I in. Why did I make it a voltage source? Because if the current is being amplified with the factor of Rm, Rm has the unit of volt per ampere. Volt per ampere. Or you can call it ohm. So Rm is showing the resistance. Current is being amplified with the resistance. So what you will get? A voltage source. You can call this voltage source as current controlled voltage source. And what you would call this voltage source? This voltage source would be voltage controlled voltage source. It was controlled by voltage and it is being a voltage only. And what will be the unit of AV? AV was volt per volt, or you can say unitless. What is the unit of Rm? Rm is volt per ampere and it is being amplified with the current. So it is being amplified, sorry, it is being multiplied with the current. That means it is multiplied with ampere only. So it is becoming a volt. So this is a voltage source. Now it is being fed to the output. So it will have some output resistance as well. It will have some output resistance as well. And then there will be this V naught. So basically this much of portion, this much of portion is your transresistance amplifier. Now at the output you are having some load RL, and in the input you are having a current source, you can make it a ground. Basically this will be also grounded. Why it is grounded? Because you are feeding the amplifier with some input only. So the input resistance will also be grounded, and that is the current is being amplified with the factor of Rm, and then it is being fed to the output, right? So tell me, what will be your I in? What will be your I in? What will be your I in? I in would be Rs upon Rs plus Rin into Is. Say yes or no? Because current is always divided in inverse proportion. If Is current is coming in Rs and Rin, so it will be divided in inverse proportion. So Rs upon Rs plus Rin into Is, right? And what about your V naught? What will be your V naught? V naught will simply be RL upon RL plus R naught into Rm I in. So let's write down the final V naught voltage. V naught voltage will be Rm is a gain of the amplifier, and then RL upon RL plus R naught, RL upon RL plus R naught, and I in. What is I in? I in is Rs upon Rs plus Ri, Rs upon Rs plus Ri, Rs upon Rs plus Ri into Is. What will be your V naught by Is? V naught by Is is, this is Rm, and then RLRS upon RL plus R naught into Rs plus Ri. This is your V naught by Is. So this is your final gain. Now before looking at this expression, tell me what should be the value of Rin and what should be the value of R naught for getting maximum gain. What should be the value of Rin for getting maximum gain? Rin should be as low as possible, right? If Rin is low, that means it will drive the maximum current. If Rin is low, it will drive the maximum current. Most of the part will be coming into the Rin only. Most of the part of the Is would be coming into the Rin only if Rin is low. Let's just say if Rin is 0, if Rin is short circuited, then Is will not flow from Rs. Is will completely be coming into Rin only. So Rin should be as low as possible. So for ideal trans resistance amplifier, Rin should be 0. What about R naught? This is a voltage source, right? This is a voltage source, and you want maximum output. From a voltage source, you want maximum output. You want maximum voltage here. So what should be the value of R naught? R naught should be 0, right? If R naught is 0, then what will happen? The complete voltage will be coming across the output RL. Now you can say, sir, we can also control the value of RL and RS. No, we are talking about the amplifier, so we will control only the Rin resistance and R naught resistance. So Rin should be as low as possible so that maximum current is coming, and R naught should be as low as possible so that the maximum output you are having. So the maximum portion should be going towards the output. Say yes or no. So Rin should be equals to 0 and R naught should be equals to also 0, or you can say low. Both should be low. No one will mug it up. No one will try to mug it up. In the examination, let's just say the question is coming, what should be the input resistance of voltage amplifier? What you will see, okay, input resistance voltage amplifier, voltage will be the input. We want the maximum voltage, so Rin should be as high as possible. Okay, now the question is coming, what should be the output resistance of a transresistance amplifier? Okay, transresistance amplifier. So output will be voltage. Output will be voltage. So certainly there will be a voltage source that is amplified. So you have a voltage source and output is voltage. That means your R naught should be as low as possible, so that the maximum output is going towards that. So that the maximum amplitude voltage is going towards the output, right? So this is how you can think in the examination, right? And if your Rin is equals to 0 and R naught is equals to 0, then what will be your V naught by Is? It would be equals to Rm only, because if Rin is 0 and R naught is 0, so what will happen? It will be RL Rs only and it will be cancelled. So V naught by Is would be equals to Rm only, right? So you will have the maximum gain. And what is the unit of Rm? Here only I wrote it. Unit of Rm is ohm, right? Unit of Rm is ohm. So in the examination, these kind of questions are asked in 1 mark, or they will give you four options. They will ask you what should be the input output resistance of a voltage amplifier, of a transresistance amplifier, or of a transconductance amplifier. So think about it. You can do the complete analysis for transconductance amplifier by your own. How will I show the transconductance amplifier? Think about it and tell me, how will I show the transconductance amplifier? I will show it by GM. Why so? Because transconductance, what will be your output? GM. What will be your output? Transconductance. Output will be current and input will be voltage. Output will be current and input will be voltage, right? So ampere by voltage, what you call it? Mho or Siemens, S. Mho, or you can show it by S, right? So what is the input? Input is the voltage. Transconductance, input is the voltage. Vs Rs, and you will have some output. In the load you will have the output current. In this RL you will collect the output current. This is your output. How will I show the internal structure? What will be the internal structure of GM? Certainly it will have some input resistance. Now since input is your voltage, so what will be coming here? Some voltage part only. Now the amplifier, this is your amplifier. This is your amplifier, right? So this will convert a voltage into current. It will convert a voltage into current. So voltage will be converted into a current source. Voltage will be converted into a current source. The job of it to convert the voltage into current source, right? Now the question comes, what should be the direction of current I should make? What should be the direction of the current that I should make? If this is your question, then I will ask you one more question. Why did not you ask me what should be the direction of voltage I should make? Why should be plus minus? Why it cannot be minus plus? My question is, what should be the direction of current here? If this is the question, then why I did not ask this question here? What should be the voltage direction here? Why should be plus minus? Why it cannot be minus plus? So it's just the way of showing it, that your amplifier is working such that it is giving you a voltage from plus to minus. Upper one is plus, lower one is minus. You can make an amplifier that gives you negative gain. What is that amplifier? Do you remember? That gives me negative gain. Common source amplifier. Common source amplifier gives me negative gain. And now let us assume this can be common drain amplifier. Common drain amplifier will give you a positive gain, or it can be common gate amplifier as well. That also gives you a positive gain. So the direction doesn't really matter. But if I am showing this by positive and negative, then how will I show the current? Current should be going outward. Basically, what I am doing is, let's just say this is your V and this is your resistance R. If you need to convert this voltage source into current source, what you will do? I into R. What is the direction? Direction should be such that the current is coming out of the positive terminal. The direction should be such that the current is coming out of the positive terminal. I taught you all these things in the network analysis. So the direction of current source should be such that the current is coming out of the positive terminal. So similarly, if I am showing plus minus, then I will make the current sign to be upward. Current sign should be upwards. So here the current sign should be upward. Now what will be this current source? Now amplifier is converting our input voltage to a current. So GMV in. This is the current source, and then you are feeding it to the output. You will have output, but this current source will certainly have some output resistance, and that we will connect in parallel R node, and then you are having the output RL. Well and good. This is your P naught, right? So this much of the portion is your transconductance amplifier. Let's connect the input source. Output source I have already connected. So what is our input? Input is simply Vs, and there is Rs connected to it. This portion will also be grounded. Tell me what will be your, let's just write final output voltage now, or let's write Vin as well. So what will be your Vin? Vin would be Rin upon Rin plus Rs into Vs. What will be your V naught? V naught will be R naught upon R naught plus RL into the current source, because the current will be divided in inverse proportion, GM into V. What will be your V naught? V naught will be GM is the factor, GM into V in you can write. Not, it should not be, yeah, it is GM into V in only. So GM is the different factor that you can write in the side, and then R naught upon R naught plus RL. What is your V in? Your V in is Rin upon Rin plus Rs into Vs. Rin upon Rin plus Rs into Vs. What will be your V naught by Vs? Okay. Sorry. We are calculating the output current, not the voltage. I'm really sorry. We are calculating the output current. Really sorry for this mistake. So what will be your output current? Your output current would be R naught upon R naught plus RL into GMV. So whatever the expression that I wrote previously, that was for the current. Right? GMV in. So you are calculating the output current, not the voltage. This is your output current. Look, this is the voltage V in that you are getting, Rin upon Rin plus Rs into V in. Now this is the output current, not the voltage. Let's just not show the voltage, just show the current. In the output you are having that current is I naught. That's it. Did you understand this point? Here I should have written the expression of I naught. There I wrote V naught, but that was not the expression of V naught. That was the expression of I naught only. If I need to write the expression of V naught, let's just say this is my V naught. So what will be the expression of V naught? Simply this current multiplied with RL. That will be the expression of my V naught. But here I need to write the expression of only I naught as only I naught. So I naught is R naught upon R naught plus RL into GM into V in. Right? And what is your V in? V in is Rin upon Rin plus Rs into Vs. So what will be your I naught? I naught will be R naught upon R naught plus Rs into R naught upon R naught plus RL into GM into what is your V in? V in is Rin upon Rin plus Rs into Vs. So what will be your output current divided by input voltage? That would be Gm into R naught upon R naught plus RL into Rin upon Rin plus Rs. Now, before looking at the final expression, tell me what should be the value of Rin and R naught without even looking at the output expression. What should be the value of Rin? Rin should be high or low? Rin should be high, so that the maximum voltage is coming across the Rin. If Rin is high, the maximum voltage will be coming. So, for ideal transconductance amplifier, Rin should be as high as possible. That means it should be infinity. What about R naught? R naught. Okay, transconductance. Output is current. So if output is current, that means maximum portion should be going towards the load. Maximum portion should be going towards the load. Maximum portion of current should be going towards the load. So R naught should drive 0 ampere current. R naught should drive 0 ampere current. And when it will drive 0 ampere current? If it is infinity. If R naught is infinity, that means complete current will be going towards the RL. If R naught is infinity. So for an ideal amplifier, R naught should be, for an ideal transconductance amplifier, R naught should be infinity. That's it. And if your Rin is infinity and R naught is infinity, then by this expression, what will be your I naught by Vs? I naught by Vs would simply be equals to Gm only. You can put it R naught, Rin is infinity, then it will be 1. R naught is infinity, it will be 1. So I naught by Vs would be Gm only. Well and good. Understandable? So this is how you will remember. And what is the unit of Gm? That is Maho, or we show it by Siemens as well. Well and good. Let's talk about current amplifier. So how will I show it? I will show it with the gain AI. AI. Voltage gain I was showing with AV. I am showing current gain with AI. So input is current. Now the current will be converted into current source only, and it will be fed to the output. So input is current. This is your RS. Now it will have some input resistance, and then it will generate a current controlled current source. Here what was the scene? It was voltage controlled current source. This is controlled by voltage, voltage controlled current source. It will generate current controlled current source, because input is current, output is current. So current controlled current source. In the previous case, that was transconductance. Output was current, input was voltage. So voltage controlled current source, right? It will be current controlled current source, and this is your load RL. And you are having some output current I naught. Well and good. Should show it in a better manner. So let's make the complete diagram. So if I make the complete diagram, so for the amplifier part, it will have some input resistance. In that input resistance, some current would be coming. In that input resistance, some current would be coming, and that current would be I in. Now this current will be amplified with the factor of AI and will generate a current source only, since my output is also a current source. So it will generate a current source only, AI into I in. Now this current source will certainly have some output resistance as well, that I will show in parallel. For a voltage source, I would show the resistance in series, but for the current source, I would show the resistance in parallel. And here I am having the load, that is RL. This is your output resistance, this is your output current I naught, right? This much of portion is current amplifier. And what is this? This is current controlled current source. Now at the input side you are having a current source and a resistance. There is a current source and in parallel there is a resistance, that is Rs. What will be your I in? I in would be Rs upon Rs plus Rin into Is. What will be I in? I in would be Rs upon Rs plus Rin into Is. What will be your I naught? So I naught would be, again it will be divided in inverse proportion. So R naught upon R naught plus RL into AI into I in. AI into I in. So what will be your final I out? I out would be AI I can take outside. R naught upon R naught plus RL into I in. I in is Rs plus Rin into I in. Well and good. Not I in, it should be Is. Sorry. It should be Is here. What will be your I naught by Is? I naught by Is would be AI into R naught upon R naught plus RL into Rs upon Rs plus Rin. Now without looking at the expression, tell me what should be the value of Rin and Rs for ideal current amplifier. Rin and R naught. What should be the value of Rin? If Rin is as low as possible, then maximum current will be coming. If Rin is very low, let's just say if Rin is short circuited, then the current would be completely coming here. So Rin should be as low as possible. So at the input side you want maximum, and at the output load you want maximum. At the load you want maximum, so the amplifier should not eat up anything, right? So if Rin is 0, that means maximum current would be coming. And if your R0 is infinity, that means the maximum current will be going towards the load. So you want maximum current in the load. So if R0 is infinity, you will get the maximum current, right? So if R0 is infinity, you will get the maximum current. So this is the scene. Now you can put it in the expression as well, but expression is not important at all. We will never revise the expression again. Just by looking at the expression, just by looking at the circuit, we can tell what should be the value of Rin and R0. Expression I am just writing for the notes only. That's it. For your reference only, but expression is not important. The important part is what should be the input output resistance and what is the amplifier is doing. Let's revise it. What was voltage amplifier was doing? There was a current voltage source, it was converting it to voltage source only. Trans resistance, there was a resistance, trans resistance. Output should be voltage, input should be current. So it was converting the current into voltage. Transconductance, output should be current, input should be voltage. So it was converting voltage into current source. And what about current amplifier? It is converting current into current source only. This is a current controlled current source that I have written. Yeah. So if Rin is 0, R0 is infinity, what will be your I naught by Is? I naught by Is would be AI only, right? Because R0 is infinity, Rin is 0. So this will be 1, this will also be 1. So I naught by Is would be AI only. Well and good. So these are the things, these are the 4 kind of amplifiers. Now we will write down the values, what should be the input resistance and what should be the output resistance for a particular amplifier, right? So you should be able to tell me the final answer without even looking anything, just you need to think in the brain. Okay, so voltage amplifier, what it will do, it will convert the voltage into voltage only. What should be the input resistance? Rin should have as much as possible, so input resistance should be infinity. What about the output resistance? Output should not eat up any voltage. R0 should not eat up any voltage. So maximum amplified portion should be going towards the output only. So if R0 should not eat up any voltage, so output resistance should be 0. What about transresistance amplifier? Transresistance, output will be voltage, input will be current. So input is current. So you want maximum current in Rin. You want maximum current is Rin. If you want maximum current in Rin, that means input current should be, input resistance should be 0. Output is voltage, transresistance, output is voltage. So you don't want any voltage to be eaten up by the R0 value. You want all the voltage across the load. If you want all the voltage across the load, that means you don't want any voltage to be eaten up by R0. If you don't want any voltage eaten up by R0, that means R0 should be 0. R0 should be 0. Transconductance, output will be current, input will be voltage. Input is voltage. Input is voltage. So you want maximum voltage across your input. If you want maximum voltage across your input, that means Rin should be as high as possible. So Rin should be infinity. Rin should be infinity because you want maximum portion of voltage across your input. What about output resistance? Output resistance. What is your output? Output is the current. Output is current. You want maximum current to go in the load. If you want maximum current to go in the load, you don't want R0 to eat up any current. If you don't want R0 to eat up any current, that means R0 should be infinity. Now what about current amplifier? Current amplifier. What is current amplifier? In the current amplifier, input will be current and output will be current. Now input is current. You want maximum current in the input. You want maximum current in the input. That means you want your Rin to be as low as possible so that the maximum current is coming. So Rin should be as low as possible. What about output resistance? You want maximum current in the load. You want maximum current in the load. So you would want your R0 to be as high as possible so that no current is going towards the output. So it should be infinity. Well and good. So infinity 0, 0, 0, infinity, infinity, 0, infinity. You will be able to write it down, right? You will be able to think in the examination. You will not have to draw any circuit. Just revise the lecture once again. You will be able to write down any input output resistance very quickly. Well and good. Let's move to our next topic. Our next topic will be feedback topologies. Now why did I teach you all these things? Because all these things will be used. Like I will directly using, okay, in what is the input resistance of a voltage amplifier? Input resistance of voltage amplifier is very high. So these things will be used. What is the output resistance of transconductance amplifier? So output resistance of transconductance amplifier is very high. So these things will be used there. So that's why I have taught you this. So now we are going to teach feedback topologies. Now I am going to teach one more method of showing the feedback model. This is one more method of showing the feedback model. So this is our forward gain, that is A, and this is our feedback factor beta. This is known as open loop gain as well, and sometimes people call it forward gain as well. But the terminology is not that important. Forward gain or open loop gain, and this is our feedback factor. So what was actually happening? Some V in was coming, output was being multiplied with the factor of beta V naught and was being fed to the input. So this was actually the input of a feedback path, right? Input of feedback path. Input of feedback path. Input of feedback path. And this is the output of feedback path, right? Output of feedback path. And now this is the input of forward path. Input of forward path. And this is the output of forward path. Say yes or no. Are you understanding this or not? Output of forward path. Some portion of output is coming, that is being multiplied with the factor beta and being fed back to the input. Some portion of output will be coming here, will be multiplied with the factor of beta and will be fed back to the input. That's it. So this is the alternative way. This is how we can show it. We can show it in the block diagram as well, but when there is two ports, if there are two ports, we show it like this. Some portion is coming, some portion going out. We can show it by this method as well, but we generally avoid it when we are studying MOSFET amplifiers. When we see the feedback topology of MOSFET amplifier, we generally avoid this, but we can show it in this manner as well. I will deal one question probably in op-amp part when we study op-amp. So probably in op-amp part I will deal one question where I will ask you to draw this diagram instead of this diagram. Okay, so you can wait for that question, but generally we show it like this. that this is the output of forward path, then it is being the input, then you are having the output and it is being fed back to the input. So this is the way. Now you will see some more important points. So what is the series connection of two port network? Two port network, port 1 and port 2. So this is a two port network and this is also a two port network. So I am writing two port network. So what do you mean by series connection? So what is a series connection? Tell me. In case of resistance, what is the series connection? Or in case of any element, what is the series connection? So this is your R1 and this is your output. So what is same in the series connection? Current is same. Both will have the same current. The current is same. Now let's just say I am saying that there is IS current going into it. IS current will go into it, and we know the concept of network analysis. Whatever the current any network will take, it will give the same amount of current. So it will certainly give the same amount of current. Now we need to connect it in series. So what do I want? I want the same thing to be happen. I want same thing to be happening here. That I want it to take the same current IS and get out the same current IS. I want the same thing. If both are in series, the same thing would be happening. If it is entering IS current and giving out the IS current. Now for the port 2, entering IS current, giving out the IS current. Now if I want this to happen, what should I do? The IS current is going out here, and if I connect these two, is there an issue with that? No. IS current is going out like this. IS current is going, and it is flowing like this. Is there an issue? No. And what about this? I connect these two, right? So if IS current was going into this, that means it is going out from here, right? So is there an issue with that? This is the series connection. You can do the same at the input side as well. This is also a series connection. So these are the series connection. Although we have studied in network analysis, we see it in network analysis that how you connected two port networks, but most of you guys might not have studied two port networks, but that is also not important with respect to interviews. But for the placements, for the gate examination, two port network is important. So for those who are preparing for gate examination, they might have studied what is the, this is the input current, that is the output current, and it is being fed to the input and it being getting out of it, right? Right. So IS current is flowing. IS current is flowing in this loop like this. Right. So the current is same. So same thing will be happening at this side as well, but I don't need to show it here. Now let's talk about shunt connection. So in shunt connection, what happens? Let's take the case of resistance only. Shunt means parallel. Parallel connection, or you can say shunt connection. So in shunt connection, what happens? In shunt connection, voltages are same, right? This is your R1, this is your R2. R2 is having V voltage, so R1 will also have V voltage. So both will have the same voltage. So voltages are same. Now let's just say this port is having, in the previous one we showed it at output port, so now I am showing it at input port. I can show it at input port. So if this is having some Vs, now you want this also to have Vs. So you want this and this potential to be same. You want this and this potential to be same, because let's just say if the potential here is A, so here also potential will be V. If here the potential is B, here also you want the potential to be V. Why so? Because VA minus VB is Vs, here also VA minus VB is Vs, right? You must have understood it. You want this and this potential to be same. So basically, how will you connect it? What I will do, want this and this potential to be same, so I can connect it something like this. Now what is the second thing I want? I want this and this potential to be same. So this and this potential to be same, so I can connect it with the jumper wire, that it should be coming above from him and should be connected like this. This and this potential are same. Well and good. And the same connection you can make at the output port as well. Same connection we are making at the output port as well. So at the output port as well, the same V node will be coming here. Let's just say this is your V node. What is happening? This V node, this node and this node will be same, and this node and this node will be same. This will be your V node only, right? Although there will be some feedback factor, all those things, but just I hope you might have understood what do I mean by the connections. What is the meaning of connection? What do I mean by parallel connection, and what do I mean by series connection? So how do I make a series connection? In series connection, these two nodes are connected and these two nodes are connected. In parallel connection, this and this node is connected and this node is connected. Well and good. Understood? Everything is crystal clear, right? Let's just see one more thing. So there are two terms, sampling and mixing. Sampling and mixing. What do you understand by mixing? Mix hona. Like two things are getting mixed. Fusion of two things. Prep fusion. Okay, forget about it. So sampling and mixing. Sampling means it is coming as it is. It is coming as it is. And then mixing. So at the output mode, what is happening? Here the output is being sampled. Output is being sampled. Output is coming as it is. For this gain A block, what is happening is that the output is coming as it is. Output is being sampled. Output is being sampled. Now after being sampled with the factor of beta V naught, after being sampled, it is being mixed with the input, right? Vin is mixed with the input, right? It could be Vin plus beta V naught, or it could be Vin minus beta V naught. So basically output is being sampled and it is being mixed with the input. So at the output port always sampling will be happening, and at the input port there will be always mixing. Did you understand this point? Output port there will be sampling, and at the input port there will be mixing. This is just a method to remember. This is a very important thing to remember. If you remember these things, then it will be very easy for you to understand feedback topology. Otherwise it becomes very complex. It becomes very complex to remember the names of feedback topology. I have seen a lot of students getting confused in the names of feedback topology. They don't even know what is sampling, what is mixing. So output is being sampled and it is being mixed with the input. So at the output port you will see sampling, at the input port you will see mixing. So if I say what is happening at the output port, I will again and again use this term. I will again and again use this term. So what is happening here? Here sampling is happening, and what is happening here? Here the mixing will be happening. Well and good. Understood? Let's see few more important points. What is the important points to remember? So let's talk about series connection. So in series connection, what is the same thing? Current is the same thing, right? Let's just say this is I1 current and this is the I2 current, and I current is flowing. So here I is equals to I1 equals to I2. Current is same. What about voltage? This is your V1 voltage and this is your V2 voltage. V is equals to V1 plus V2. V is equals to V1 plus V2. Voltage is mixed. Basically, you can say voltage is mixed because voltage is not same. In case of parallel connection, what is the scene? In case of parallel connection, what is the scene? The voltage is same. The voltage is same, but the current is mixed. So let's just call this as V1, this as V2. So what you can write, V is equals to V1 plus V2. So voltage same, but current is mixed. Now, why I am teaching this simple thing? Are you guys able to understand? Are you guys able to connect? So that next things will be easy for you, because if I say series connection, what should be coming into your mind? That current is sampled, voltage is mixed. If I say series connection, what should come into your mind? The current is sampled, because current is same here. The current is sampled and voltage is mixed. So series connection means current sampled voltage and voltage mixed and voltage mixed. And if I say parallel connection, what should come into your mind? Parallel connection, that voltage is sampled, and current is mixed. Right, because that is the parallel connection. Voltage is sampled and current is mixed. In parallel connection, current are different, but voltage is the same. Same means sampled. Why same means sampled? Because I told you the output is coming same as it is. So output is being sampled and it is being mixed with the input. Right? So when I say series connection, it should be striking in your mind that current is being sampled and voltage is being mixed. Let's just check out here. If I talk about series connection, so what is happening? Whatever the current you are having here, the same current is being fed to this part. So here what is happening? Here current sampling is happening. Current sampling is happening. Now in this case, what would be happening? At the input side, we always have mixing. So here there is no current mixing. Why there is no current mixing? Because whatever the current you are having, the same current is going into the input. Whatever the current you are having, the same current is going into the input. So there is no current mixing, but there is voltage mixing. How there is voltage mixing? Let's just assume I apply a Vs voltage here. So now this current will be converted into some voltage. Let's just assume the current is converted into some voltage. Let's just assume this current is converted into beta into I voltage. This is a voltage, beta into I, or I should write Rm into I. This current is converted into Rm into I voltage. Now this Rm into I voltage will be going here as well, because this node is this node, these two nodes are same, and this node is same. So this voltage will be Rm into I here. Now what will be this voltage? This voltage will be Vs minus Rm into I. This voltage will be Vs minus Rm into I. So here voltage is mixed, but current is the same thing. So in the input side, we are not going to see the sampling. In the input side, we only need to see the mixing. So what is being mixed in the input side? So in series connection, if at the input side you are seeing the mixing, that means that is the mixing of voltage. So I know this is sounding a bit typical to you, but gradually you will understand. There is no issue. Gradually, slowly, if you don't give up on this topic, you will understand everything. Slowly we will build the concept. No worries about that. We will see different topologies. We will make this diagram again and again, and you will be habitual. So don't give up on this topic. Just study it, and in the end you will be very, very comfortable, right? So for a two-port network, this is our network. This is our two-port network. I told you one thing, that at the output port you will always have the sampling. At the output port you will always have the sampling, and once it is sampled, it will be mixed with the input. So at the input port you will always have the mixing. You will always have mixing. So these things you can remember, right? Now let's decode it. Decode the following. Okay, if I am saying voltage is sampling, then is it a series connection or shunt connection? If voltage is sampled, forget about input output, I am just saying voltage is sampled. So is it a series connection or shunt connection? Shunt connection, because voltage is same in case of shunt connection. So this is a shunt connection. Shunt connection. Now the next thing I am saying, current is being mixed. Current is mixed. If current is mixed, then it is a series connection or shunt connection? Current is mixed in shunt connection. So it is a shunt connection. Now next thing I am saying is voltage is mixed. Voltage is mixed. Voltage is mixed in series or shunt? Voltage is mixed in series, because in shunt voltage is same. So series connection. Now let's talk about the other one. Current is being sampled. Current is sampled in series or shunt? Current is being sampled. Current is same in case of series connection. So this is a series connection. So we have decoded these four things. Slowly we will decode everything. Now series connection. If I am saying series connection, So what do you understand by series connection? Voltage mixing, voltage sampling, current mixing, or current sampling. There are 4 things. In series connection, 2 things will be happening. So in series connection, what happens? Current is being sampled and voltage is mixed. So if I say series connection, what should come into your mind? Series connection, okay. Current will be same. So current sampling, and voltage is different. So voltage mixing. You need to put your whole concentration on this topic only, then only you will be able to understand. It is not MOSFET amplifier that GM in current is coming. No, it is a complex topic and many teachers ignore it, and a lot of students I have seen getting confused in this one. So you should be able to grasp this topic if you put your complete concentration. This is the easiest way of remembering all kind of feedback topology. This is my guarantee, right? So current sampling and voltage mixing. Shunt connection. What do you mean by shunt connection? In shunt connection, voltage is the same. So voltage sampling. Voltage sampling and current mixing. Now decode the next thing. What is the next thing? Series connection at input. At input. First, I need to think at input. At input, what happens? Mixing. At input, mixing takes place. At input, there is no sampling. At input, there is only mixing. So if there is mixing at the input, and that is series. So in series, what is mixed? Voltage. In series, voltage is mixed. So if there is series connection at the input, that means it shows the voltage mixing, right? It shows the voltage mixing. Now series connection at output. At output means it is certainly sampling. It is certainly sampling, right? If I am talking about output, it is certainly sampling. So if series connection is there, in series connection, what is sampled? In series connection, what is sampled? Current is sampled. So this is current sampling. So if there is series connection at the output, then current will be sampled, right? Shunt connection at input. If at input, that means it is mixing. If you are talking about input, that means it is mixing. Now, what is mixed in shunt connection? What is mixed in shunt connection? Tell me. In shunt connection, current is mixed. So it shows current mixing. So if you have shunt connection at the input side, that means there will be current mixing. That's for sure. If you have the shunt connection at the input side, there will be current mixing. Shunt connection at output. Shunt connection at output. Output means sampling. Output means sampling. So what is sampled in shunt connection? What is sampled in shunt connection? What is same in shunt connection? Voltage. So this shows voltage sampling. So slowly are you getting to the point why I am teaching these things? In the next lecture, it will be all clear why I was teaching all these things. In the next lecture, we will see voltage sampling, we will see series shunt sampling, we will see shunt sampling, we will see shunt series, we will see series shunt series. So everything we are going to see in the next lecture. So it will be all clear in the next lecture. What is the meaning of voltage mixing? What is the meaning of current mixing? What is the meaning of current sampling, voltage sampling, series connection, shunt connection? But till now you understood few points. What are those points? That at output side there will be sampling, at input side there will be mixing. If I am talking about sampling, if I am talking about series connection, what do I mean by series connection? In series connection, current is sampled and voltage is mixed. If I am talking about shunt connection, in shunt connection, the voltage is sampled and current is mixed. So this is the conclusion that you have studied till now. So I will write the conclusion. That's it. I will write the conclusion. So shortly I can write the conclusion. What you have studied till now. So first point, at input you will see mixing. At output you will always see sampling. If I talk about series combination, in series combination current is same. So current sampling and voltage mixing. And if I talk about shunt connection. In shunt, what is same? Voltage is same. So voltage sampling and current mixing. That's it. Only these are the points which you have studied till now. Only by using 3 points you can completely understand the feedback topologies. Otherwise it becomes very difficult, very confusing as well, that what is being sampled, what is being sampled, what is being mixed. By looking at the block diagram you can understand it more clearly. So in the next lecture we will look at the block diagram, how voltage is being mixed, how voltage is sampled, how current is being mixed, how current is being sampled. So in the circuit diagram, in the block diagram it will be more clear, but in theoretical this is the same. So theoretical thing we have already studied. Now we will see the circuit diagram. It will be more clear to you. Okay then, thank you. Let's meet you in the next lecture.